Good morning, everyone, and welcome to this last day of the SATURN conference this year. The conference organizers wanted me to remind you of a couple of things. One of them is that you need to fill out today's evaluation forms, which are here, and also the conference evaluations, which are also here, because it's very valuable to people that organize conferences when they get feedback. That means they can improve for next year. So, this session, I'm Harold. I'll be hosting this session for JR and Rick. Today we'll talk about security design refinements. When I asked them how they wanted to be introduced, Jungwoo said he wants to be called JR, and Rick said he wants to be Albert. So Albert and JR,
easy to pronounce.
Away.
Thank you. Okay, so welcome everyone. I'm sure you all realize that you are in a participatory session, which means that we only do half the work here. Half the work is going to be done by you guys, and hopefully this will be a good opportunity for learning and for discussion, and that is our objective. So what we're going to do is have a really quick introduction to the basics of software security. And this is not meant to teach you software security. If you don't know anything about software security, then you may be a bit lost. It's simply to establish a common vocabulary and common motivation for us to talk about secure software design. How do we, as architects, respond to security threats? How do we even figure out what they are? And then how do we design to meet those? How do we prioritize them? We'll talk about a method that we've developed called architecture analysis for security that helps you think strategically about security, about the design decisions you have made or not made to achieve security. And then we'll have our actual hands-on session where you guys will be trying to identify the relationship between security tactics and patterns. And the purpose of that exercise is to get you to think about the underlying objective of a pattern. What is it it's trying to achieve? How does it achieve it? And does that give you the level of security that you may need? So we're going to be just talking 10 minutes, super quick introduction to the basics of software security. We'll have a few minutes to just discuss any questions, vocabulary, understanding issues. And then we'll go into a little more lengthy discussion about how you architect for security, how you design for security, and the AAFS, as we call it, the AAFS method for analyzing. And hopefully, if you're attending SATURN, I don't have to convince you that design and analysis are two sides of the same coin. So whatever decisions you make in design, you need to analyze those decisions in analysis, and it's essentially the same kinds of intellectual basis for both activities. Hopefully you'll see that. So once we go through that, we'll have half an hour for your work, where you're going to be mapping tactics to patterns, and then we'll wrap it up with 15 minutes of discussion. So to begin with, as I said, I'm going to just do a very quick introduction to security. Hopefully I'm preaching to the choir here, and you're all going to nod your heads, and we won't get any fights. So first of all, it's important. Everybody nodding? Yes, it's important. So our society runs on software, and we depend on that software being trustworthy for our health, for our transportation, for our commerce, for every aspect of society. And there are threats out there. Those threats are real. Hardly a week goes by where you don't hear about some august institution being hacked. According to a report from IBM last year, they said the average data breach security average had a cost of $3.8 million, and they pegged the number at $154 per data record stolen. And sometimes there are thousands, millions of data records stolen. This is big business, if nothing else, and certainly it's more than that if there are safety critical issues, if so much of our infrastructure depends on software security. We heard some talks about Internet of Things, and the security issues with Internet of Things are kind of mind-boggling. So software has bugs, right? We all know that. That's just the life that we live. And those bugs may arise from an implementation problem. So somebody makes an off-by-one error in a loop, or they forget to terminate a string, or they forget to terminate a buffer, or they allocate memory and then don't dispose of it properly, or they're not filtering input properly. And those may come from design flaws. So it may be that you, as a designer, didn't think about the number of entry points into a system and have not treated all of those entry points equally, or have not secured all those entry points equally. And those design flaws may be exposed naturally just by the random activity of users. Something bad may happen. Or they may be exposed artificially, and that is typically called an exploit. That's the world of a hacker. A hacker wins when he exploits a flaw in your software. And of course, this is our focus. Both are important, but this is typically what we really have to worry about and what we have to try and understand and defend against. The sad state of software today is that we don't do a good job at this. We don't do a good job in general, as in software engineering, at managing defect rates in software, and another talk, but I think a great deal of the blame for that goes into the fact that we pay little attention to architecture, pay little attention to design flaws, and so it's very difficult to debug software when you're down in the weeds, and in fact it's your bad design that is causing your software to be excessively complex and confusing. But if we focus specifically on flaws that affect security, often these creep in because security isn't a priority. Features are a priority. Time to market is a priority. Security is a band-aid. Security is layered on afterwards. Security is an afterthought. And quite frankly, like many quality attributes, considered a financial burden. Well, let's get the system working, and then we'll make it robust. Then we'll make it usable. Then we'll worry about scalability. Then we'll worry about making it evolvable or maintainable. And this, of course, is a burden, becomes a burden eventually for the project. So if you are thinking with a security mindset, then what you're trying to do is to think about how your software can be attacked. What are the attack vectors? What are the threats? And to try and prevent those by reducing the probability of both implementation bugs and design flaws. And again, our focus is going to be on the design flaws. It's never going to be perfect. It's never going to be done. So we cannot make that our goal as practical software engineers, practical architects. We want to make the hacker's job hard. We want to make the hacker's job as difficult as possible so that the losses that you experience are minimized. So we're going to talk about software defects. We're going to talk about software bugs, flaws. And so just to get a common understanding of those terms, a defect, what we're calling a defect, includes both design vulnerabilities and implementation vulnerabilities. A bug is just a simple implementation error, like I said before, perhaps an off-by-one error, perhaps you're using a an old version of an interface which is more vulnerable to attack. Whoops. A flaw is usually something deeper, like I said before, perhaps too many access points, perhaps you're doing input filtering inconsistently. You'll see this in the case study that JR will introduce in a little while, that there was a big system and they were having significant security problems due to SQL injection attacks and cross-site scripting attacks, and it all came down to this in the end. They didn't have a consistent way of filtering input, and that was really a design flaw. It's that the architect didn't think about that when creating the initial design. They were rushing to market, they were worried about implementing functionality and getting the features that users wanted, and really this was an afterthought. And so it was missing in the design. So given that we're never going to have secure software, completely secure software, we as architects have to think about what are the threats that we're facing and attempt to design strategies for what we think of are the biggest threats. And so you need to think about risk exposure, and risk exposure is the probability of a loss times the size of a loss. So a data breach, a major data breach, may be relatively rare, but it has an enormous consequence. There's an enormous size to that loss. An individual user having their password hacked, just an ordinary user, not a super user, might have a relatively small consequence for the system, but its probability is going to be significantly higher. We have to think about the aggregate, the product of those two factors, to figure out which are the risks that we're going to protect against, and then we're going to decide, are we going to put more of our architectural dollars, more of our architectural brain power into worrying about data breaches, or putting really heavy-duty multi-factor authentication in to guard against each of those threats. So what is it we're trying to achieve in security? Typically people talk about CIA, confidentiality, integrity, and availability. So confidentiality, that says only authorized users have access to privileged information. Integrity says that only the right people can modify that information, can remove that information. And availability says that the resources are there when I need them to be. And you'll see that we're going to talk about a few more kinds of threats, but all of them can be traced back to one of these root goals in a system. Okay, so that's the 10-minute intro to software security. So anybody have any thoughts about that? Observations, questions, clarifications? Yes.
You talked about you talked about the product of the probability times the impact. Some companies use a 5x5 matrix. One axis is probability or likelihood, and the other one is the consequence. And sort of examine them individually as to where they land in that 5x5 space. Do you have any comments on that approach versus just a pure product?
Sure. So I believe the reason that some companies do that is essentially both of those values, the probability of a loss and the size of a loss, are difficult to estimate. And so when we do an ATAM, for example, and we ask users to rank scenarios, we'll ask them to rank them as high, medium, or low. And this is essentially the same thing, a 5-point scale, a 3-point scale. So people can't say, yeah, I think the probability of this loss is 22%. It's just, well, it's pretty low. And this other one is not 89%, it's pretty high. And so I think that that's a reasonable heuristic to get at a way of prioritizing in the absence of hard data. If you've collected a lot of data in your organization about data breaches over a decade or something like that, perhaps you can assign precise probability, but very few organizations have that kind of data. And even if they did, well, this system is different. So it's still at best an estimate.
Also, comment or question related to the risk assessment. In our organization, we are also doing the probability as a product of detectability and probability of occurrence, which also channels some of the countermeasures potentially as, you know, being risk or the potential flow being detectable. Do you experience this with other companies or?
So that's an interesting take on it. And in fact, you'll see when we start talking about the security tactics, the first category is detecting an attack. A lot of people don't even think about that or don't worry about it. They just somehow assume that when they're attacked, they're going to know it. But you know that's not the case. There are well-publicized examples of data breaches where the company, 2 or 3 days after they were breached, figured it out and then, you know, sprang into action. So as I said, this is a basic introduction, and I was just introducing that as a conceptual model for thinking about it. But yeah, absolutely, you have to think about both detecting the attack and actually responding to the attack. It's a reasonable way of thinking about it. And in fact, you need architectural strategies for both. Okay, so let us carry on. So now I'll talk for a few minutes about the fundamentals of secure design. And again, it's just a few minutes, so we're going to be sketching at this point, and part of the exercise that you guys will be doing is to worry about some of the details. So as we said, to design in security, you first have to figure out what your risks are. One of the ways that I like to do this is to use the STRIDE threat model to enumerate risks. And STRIDE is a model that was created by Microsoft. I think it was in 2009. The acronym is just the first letters of 6 categories of attacks: spoofing, tampering, repudiation, information disclosure, denial of service, elevation of privilege. Why use a threat model? Well, what's the alternative? If you're an architect, how do you decide what threats your system may be facing? The reality is, in speaking with the architects that I've spoken with and that the architectures that I've analyzed over the years, is that architects tend to, if they build insecurity at all, they build insecurity to address the things that have bitten them in the past. The stuff that they're thinking about, whatever's on the top of their mind, their burning issue. And this isn't really a good engineering basis for surveying the field of possible threats, because the fact that you've been bitten by one kind of threat in the past doesn't mean a different kind will bite the next system or the next release of the next system that you're creating. And so the nice thing about STRIDE is it helps to ensure coverage, that you've at least considered different categories of threats and how they affect the system. So each threat type violates some security property. So a spoofing attack, the way you spoof, you adopt an identity that isn't yours, is you have essentially violated the authentication property of the system. You can't spoof without fooling authentication. Or for tampering, you're tampering with some data in the system or data in transit, then you violated the integrity property of the system. That data should have integrity. Repudiation violates the non-repudiation. So non-repudiation is the idea that if I make a transaction on the system, I cannot later deny having made that transaction. I can't cover up my traces. Information disclosure violates confidentiality. That's pretty obvious. Denial of service attacks are violating the availability problem. If I attack a system, if I mount a denial of service attack on a system, I am either crashing the system or I am lowering its ability to respond to the legitimate users of that system. So that's an availability property that I'm attacking. And elevation of privilege, the idea that someone can come in and get, let's say, root privileges within a system, violates the authorization property. They are now gaining an authorization to which they're not legitimately eligible. So to design in a security property, our claim is that you need an architectural strategy, that you're not going to hack your way to these properties. You're not going to grow them organically. You're not going to grow them by code and patch. That you need a strategy. So that means as architects, we need to think about these early on, and the way that we promote thinking about them is via patterns and tactics. So begin with design strategies to address classes of attacks, classes of threats, and then of course you have to flesh those out in terms of their realization as code, as frameworks, as components, some form of implementation. So our job, excuse me, our job this morning is to reason about tactics and patterns and their relationships so that we understand them better and we understand what they're for. So none of you, hopefully, need an introduction to patterns. They are recurring, useful solutions to recurring problems that architects have. They are found repeatedly in practice, and that's why we know that they're good, we know that they're proven. However, there are thousands of patterns, and they're documented across lots and lots of patterns. Oh, and also, I don't ever worry about what's a design pattern and what's an architectural pattern. That's not an interesting debate as far as I'm concerned. We can talk about that offline if you're interested, but we're not going to worry about that now. So there are lots of pattern catalogs out there. There are many, many books. The Patterns of Software Architecture series alone has 6 volumes. There are websites full of patterns. And here we're going to focus in on security patterns, which are well-known solutions to recurring security problems. So we're just going to zoom in on that part of the patterns corpus. And our claim is that security patterns are refinements of and instantiations of security tactics. Security tactics are the primitive design operations that you can use to achieve security. We like to say that tactics are the atoms and patterns are the molecules. So if that is true, if that analogy holds, if tactics are atoms, then it's like the periodic table. They define the entire space, the physics of what is possible, of what you can possibly do to achieve security. And patterns are then the interesting combinations of those that have combinations of properties that are useful in the real world. Patterns are closer to code. Part of the process of documenting a pattern often is to say, oh, here's a class diagram, here's an example, here's a snippet of code, so you can actually see what you would do to implement that. And there have been hundreds of security patterns, hundreds, just for security patterns, documented. So it's still a big space, and in part this is why we think this exercise is useful, because when you're faced with hundreds of anything, the question is, oh my God, well, which one do I use and where and why? So hundreds is not actually that useful if you cannot distill them down to their root purposes. So again, books, websites, blogs, there are lots of things out there that you can read, and these are really nice books. I like all of them. My only problem with them is TMI, right? Too much information. How do I choose? So our solution is to begin by thinking about tactics, because tactics are the atoms. Tactics are more primitive. They're the things that compose those molecules that are patterns. So this is our current set of security tactics. It has been around with relatively few changes for more than a decade now, but it does evolve. Just like there's no complete final set of patterns, there is not and likely never will be a complete and final set of security tactics. But what we can say is, like the periodic table, you expect a new element to be discovered relatively rarely. And it probably does not rock your world when that happens. It's, hopefully this has covered the majority of the landscape. So when we describe tactics, we begin with the design goal, the design intention. There are tactics to detect an attack, to resist an attack, to react to an attack, and to recover from an attack. And as an architect, if you want to design a secure system, you have to at least consider all of these categories. How do I even know that I've been attacked? How do I discover it? It's not obvious, and as I said, there are systems where they don't figure it out for hours or days. How do you distinguish a denial of service attack from a really successful day at your e-commerce website, right? Once you've detected that you are in fact under attack, however you've detected that, whether the system told you or it was some user complaining, you then have some opportunity to resist those attacks, to make it harder for someone to attack you. And sometimes this will fail. You will not resist an attack. So now you have to think about, well, what are the defensive measures that I can put in place now that I know that I'm under attack? And finally, when those things don't work, you have to recover from an attack. You may have to do things like you do in availability. You have backups and spares, hot spares, warm spares, cold spares, failover, and so forth. And you may need to, hopefully you've got an audit trail, and you may need to look at that audit trail both to recover information, to figure out what information might be corrupted, and maybe to help the authorities go after the bad guys. So the nice thing about tactics, if they are correctly construed, is that this covers the landscape. This is the landscape of what is possible as an architect from a strategy point of view. What do I need to think about? What do I need to do as an architect? This is an implementation, of course. We now need to move a step closer to implementation, and that's why we do this mapping from tactics to patterns and from patterns to implementation. And that's how we gain intellectual control over the process and make this not something where somebody poses a difficult problem to the architect thinks hard, architect presents the solution, right? That's the alternative, is all of us architects have to somehow be wizards and we just intuitively know what to do, and that's just unrealistic. So if we want software engineering to be a true engineering discipline, we have to define what are the primitives and how do we map from those primitives, those concepts, to implementation, and that's what we're trying to achieve here. So with that, I will turn it over to JR, who'll talk about the AAFS method.
So architectural analysis is really the focus of this AAFS method, and architectural analysis, as you know, really this structured way of discovering either the absence or presence of these critical design decisions in software architectures, especially in terms of quality attributes, such as, of course, security, maintainability, and so on. So a lot of times what happens is when we develop software, we always tend to jump into coding prematurely. And of course, the recommended practice is always to go through this process of architectural analysis and try to build, for example, security into the software. But then, unfortunately, a lot of times that doesn't happen, and the consequences could be really severe. And some of the consequences could be including disruptions, cost overruns, and especially in terms of security, when you don't think about security during your architectural analysis process, you end up with a lot of security vulnerabilities in the end. So architectural analysis is really critical in this case. So there aren't too many architectural analysis methods out there. I mean, you're probably familiar with Atom, but nothing else probably too much. But not to mention architectural analysis method dedicated to security. And what we are really trying to do here is to develop this architectural analysis method dedicated to really analyzing the security aspect of your software. And security is becoming, important more and more every day because, again, the consequences are really grave. So one of the core ideas behind our method, ops, is really that leveraging these design building blocks, such as tactics and patterns, as Rick mentioned earlier. And we try to really zoom in on these different aspects of security so that we can really identify some of these problem areas very easily and in a very effective way. And our method consists of these three different parts, starting with tactic-oriented architecture analysis and pattern-oriented architecture analysis. And you can see the tactics and patterns are embedded into the method. And then finally, we also take a look at the vulnerabilities, because vulnerabilities, in this case, we look at it as, I would say, the symptoms of these missing design decisions, especially in terms of thinking about security tactics or security patterns. So when you don't really consider these things early on, the symptoms or the consequences of not thinking about security show up as vulnerabilities. So this is just one more way of looking at the software and trying to see if there is really this set of problems showing up. And one of the mechanisms, the core mechanisms we're using to really do this analysis is doing these interviews with the architects. So let me just talk a little bit more about the role of tactics and patterns so that you have a better idea of how they help with our architectural analysis. So as you know, these tactics and patterns are mainly design techniques really to help with coming up with the design solutions. But we had this aha moment because, as Rick said earlier, we may be using these design building blocks as our tools for architectural analysis. So in this case, we're really trying to leverage these tactics and patterns as our way of analyzing software architectures. And as I said earlier, vulnerabilities are also very important in our case. So when we talk about vulnerabilities, they mainly refer to these weaknesses found in your software, and especially at the code level. And there are mainly two major vulnerability databases out there available. And you may be already familiar with some of these. So common vulnerabilities and exposure, CVE, is one. And another one is common weakness enumeration, or CWE. And like I said again, let me reiterate this point, because these vulnerabilities are really important to us, because this is how we double check whether, for example, these design ideas, security design ideas like tactics and patterns, are fully and faithfully implemented in your code. So going a little deeper with CVE and CWE here, for those of you who are not very familiar with this. So CVE is really referring to these individual security incidents reported to the database. So the number is pretty high. So we have right now 70,000 and more CVE entries and counting. And CWE is really categorizing these security incidents into different types. So for our purposes, to really connect the vulnerabilities to the patterns and the tactics, we really think CWE is much, much more appropriate, just because of the number out there. So we have about 940 entries out there. So just to give you an overview of our approach again, in general, we try to really accomplish this goal of identifying, because that's really what architectural analysis is all about, identifying either the absence or presence of these design decisions, especially in this case with respect to security as much as we can, using tactics and patterns, and using these two first phases of our approach, tactic-oriented architectural analysis and the pattern-oriented architectural analysis. And then finally, we also try to check, double check, because we want to see all the way throughout the code, these design ideas are actually implemented or not. Because, I mean, you may have a great idea, but if you're not executing your idea, then it's almost good for nothing. So in this case, that's what our vulnerability-oriented architectural analysis is all about. So just to give you a little more detailed ideas of our approach, we typically start with tactic-oriented architectural analysis. Just because the time it takes for us to really go through this phase, because we try to do it very quickly, it usually takes probably about an hour of interview with the architect. So definitely very lightweight. And then we move on to the pattern-oriented architectural analysis, because what we are trying to do here is we want to see whether these tactics, the initial ideas of security, are really refined into something much, much more concrete and closer to the code, which are patterns. And if they stopped right at the tactics, then again, you're not really doing justice in terms of security. And finally, because of the reasons I already mentioned, this vulnerability-oriented architectural analysis is critical. So let me just tell you a little bit about our case study, because until you actually try this on a real-life software application, you don't really understand, I guess, some of the flaws or the effectiveness of your approach. So we actually worked on a case study using a software project called OpenEMR. And OpenEMR is an electronic medical record system. And it's been around since 2001. And it has about 531,789 lines of code. So it's definitely not a toy kind of program or application. And it has relatively big user base. So the nice thing about this project was that we had very close access to the architect, because our method really relies on really this close relationship with the architect. This was one of the major motivations of why we used this as our case study. So again, let me go through that three-phase step process here, starting with tactic-oriented architecture analysis. And we conducted this interview with the architect regarding where and how these tactics are used throughout the software. And then we moved on to, for example, also talking about particular design solutions the architect either developed or had in mind. So what were the assumptions the architect made, or what were the rationale if they had any sort of particular security solution in the software. So just to give an idea of the question we asked, here, for example, we asked the question of, have you ever really considered or done anything in terms of verifying message integrity? And the architect's answer was sort of not very exciting. I mean, we thought about it, we did a little bit of it, but maybe not in a very systematic way. So this sort of indicates the way it's done is a little bit ad hoc right there. So we had some suspicions right there. And then we moved on to this pattern-oriented architecture analysis. And during this process, the idea was, again, like I said earlier, we are trying to see if this original tactic got further developed into more concrete idea of a pattern. So in this case, the tactic was verifying message integrity, but we wanted to see if the architect thought about developing this idea further into a specific pattern, which is, actually in this case, intercepting validator. So this is why the exercise of mapping the tactics and the patterns is so critical, because if you don't make this step, you're just stopping right there at the tactic stage, and then you end up not really implementing these great security ideas in your code. So just to give an idea of what intercepting validator is, it's essentially something that really looks out for all the user inputs, and if the user inputs are suspicious, then it will simply reject it, or if the user input is acceptable, it will pass it on. And then when it comes to the vulnerability-oriented architectural analysis phase, now it's time for us to really think about the potential symptoms. And in this case, we already sort of know, because the architect didn't even do anything in terms of intercepting validator, we definitely know there may be no implementation at all of that pattern, and no systematic way of dealing with especially user inputs. But we also still wanted to see if there is any sort of evidence of these individual developers, trying to do something about security, especially in terms of input validation. So in this case, we try to relate these. In this case, the pattern is intercepting validator. Try to relate this to specific vulnerabilities. And the vulnerabilities are turning out to be CWE89, the ones that are closely related to the intercepting validator. Those ones were improper neutralization of special elements used in an SQL command. I mean, in layman's term, this is SQL injection vulnerability. And then another one was CWE87, improper neutralization of alternate cross-site scripting syntax. So again, to simply put, this is cross-site scripting vulnerability, all related to not handling user inputs securely. So our way of looking at this was really to look at the code to see if there is any sort of evidence developers trying to deal with these types of vulnerabilities. So just to summarize the analysis result, we started with tactic-oriented architecture analysis, and we had a suspicion of this tactic, for example, verifying message integrity, not being fully addressed. And then that suspicion got a little stronger during the pattern-oriented architecture analysis, which indicated that the architect didn't do anything in terms of really developing that idea further into this pattern called intercepting validator. And we also tried to look at the code of the project to see if there was even anything done by the software developers individually. So in this case, there could be software developers maybe smarter than the architect. Maybe not the case. So the conclusion here is really there were some evidence of developers trying to address input validation or intercepting validator related vulnerabilities, but majority of those attempts were ad hoc in nature, and there wasn't really anything systematic about it. So to confirm our suspicion, we actually tried to use this commercial grade static analysis tool called the FScan, IBM product. And we tested these two versions of OpenEMR, 3.1.0 and 4.1.2. And we tested it for SQL injection. And as you can see, it started with 96 SQL injection vulnerabilities, and then ended up in the later version with 12 SQL injection vulnerabilities. And this is purely due to the, heroic efforts by the software developers, not really done by the guidance of the architect. But again, it's an ad hoc type of approach. So that's why they couldn't really completely eliminate all the SQL injection vulnerabilities. And then in terms of cross-site scripting, we didn't find any evidence of, software developers trying to really address that problem. So that's why, in between the two versions of the software, we still have, no significant change. So that concludes my part of the talk.
Of course.
I understand the applicability of the protective or detective tactics in your pattern. How about the reactive tactics? Because they can be, the pattern for reactive tactics can be very specific for, let's say, the problem. For example, banking system under attack usually fails close. And medical device, patient care device, needs to fail open by definition, cannot protect the lockout of the operator of the medical device. So do you have also the examples or patterns for the reactive tactics?
So our methodology, the AAFS as an analysis methodology, is trying to look for traceability. So we're not enumerating all possible patterns. As I mentioned before, it's not really possible because they're always being generated. What we would be looking for is an argument from the architect saying, this was my goal. This is how I want to detect, resist, react to, recover from attacks. And I realized that by the following patterns. And those patterns, as you say, might be different in a healthcare application and a commerce application because the requirements obviously are different. But we would like to see evidence that they had an architectural strategy. So in the case of OpenEMR, there was no architectural strategy. Yeah, maybe some developers did the right thing in some places, but there was no consistent strategy. So we would like to trace that or identify the lack of that traceability. And then if they have, whether they have a pattern or not, we want to look at how their response is instantiated in code. So in some ways, I'm not answering your question because I can't say that we've enumerated all possible patterns, but we have an approach that allows us to connect the dots and say, yes, you have a rational approach, and here's how we validate it. Yep. Yes. We need the microphone.
So you stated you saw inconsistency.
Hello? Yeah, okay.
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 You saw inconsistency among the developers as far as some knew what to do versus some didn't. Do you see that as a leadership issue as far as did you identify any type of leadership issue when you see that, like, okay, somebody's not talking to somebody else, who's in charge to really make sure there's consistency across the development area?
Right, yeah, that's a great question. I always say that an architect's role is 50% marketing. And that marketing isn't just to customers or product managers, but is also to the development team, getting them to believe in a particular vision, a particular way of doing it. And an area of research that's really increasing these days is this idea of looking at socio-technical congruence. Are the people that need to be talking actually talking to each other and so forth. So an architect can play a big role in that, but if the architect did not create a strategy to begin with, all the communication in the world isn't likely to achieve a high level of any quality attribute. So for example, if you think about performance, if I don't have policies and interfaces to do resource management, I've got to run around and talk to every one of my developers and say, oh, make sure you don't use too much memory, or make sure you don't use too much CPU over here. It's not a very scalable solution. So communication, absolutely important, not enough. Good communication by itself isn't enough. You need an architectural strategy.
In your analysis, do you actually look at security requirements? Do you back up and say, well, what was the customer or the product organization looking for in terms of security characteristics and security mechanisms in the architecture and design? And Do you look at, how well does the architecture actually solve these things? And if there's insufficient security requirements in the requirements documentation, do you say, are the architects actually pushing back on the product organization to say, hey, get us some more security requirements so that we know what you're looking for?
Yeah. So that's for sure in a holistic approach to security, you've got to look at that and you've got to say, did we even think of the right stuff? That's why I was advocating starting with something like a stride model instead of just the architect starting with their own hunches or based on where they've been burnt before. In AAFS, we don't do that, although it tends to emerge as we go through the tactics-oriented architecture analysis. So some of you may have heard me explain this anecdote before, but I was doing a tactics-based analysis of security with a guy who he was telling me that they had a requirement to not send, it was a distributed system, and they had a requirement to not send information from one part of the system to another in the clear. And so when we were doing the tactics-based analysis, I'm asking him about encryption, because that's one of the tactics. And he said, yes, we do encryption. And I said, what exactly are you doing? And then he got kind of sheepish. And he said, well, actually, we XOR the data. Right. So that made it clear that they didn't really have a requirement, a proper requirement for encryption. They had a vague requirement, and that the tactics-oriented analysis exposed that and revealed that, and a risk was identified in a few seconds.
Okay.
So it's not an explicit part, but it tends to arise as a result of walking through the tactics.
Okay, I like that.
Okay, so I think we're ready to move on to our exercise. So, the first part of our exercise is we would like you guys to form into teams. There's, looks like around 20, 25 people in the room. So maybe if you can get together with 4 or 5 of you together and form into a team. And within that team, don't take a long time to do this. Just select one person to be your spokesperson and one person to be your scribe, so that we're going to hand you out some materials, so you need to write some stuff down, and someone will, it could be the same person, someone will have to speak for the group. So JR is going to hand that out.
And then maybe you could form another team here together. Yep. So I think we have about 5 teams.
We have 5 teams,
Yeah.
okay. So we're going to have to double up on one. Okay, so let's see. You guys are a group. You guys are a group. 2, 3, 4, 5?
Yep.
Yes? Okay, so let's say,
I have 2 if you need an extra.
okay, does anyone need the tactics worksheet? No. Okay, so let's say that this group and this group, you're both going to be team 1. I mean, you'll be separate teams, but we only have 4 different teams in our instructions. And you guys are team 2, team 3, and team 4. We had to make assumptions. We didn't know how many people would show up. So what we would like teams 1, to do is to look at these tactics. They're all part of the detect attacks category, and write down a definition and an example. Sorry, not a definition. We've given you a definition. Write down an example of each one from your experience of how this might manifest itself.
So in the back of your handout, there is this document defining all the tactics.
Just a very brief, concise definition. So for team 2, you're going to be working on resisting attacks. So there's a group of resisting attacks for identifying, authenticating, and authorizing actors, as well as limiting access and limiting exposure. That's team 2. For team 3, you're going to also do resist attacks, but 4 different tactics from the resist attacks category. And team 4, you're going to do the react and recover from attacks tactics.
So in summary, yep.
Ooh,
That's what I
ooh, you're
did.
good.
Yeah.
Okay, so take about 5 minutes, and then we're going to discuss and then move on to the second part of the exercise.
Turn it off too.
Hey, hey.
Okay, so let's just review. We've got one more exercise for you, so we don't have time to review everyone's answers, but if you have any thoughts, comments, observations just from that you'd like to share. I'm just trying to find the examples of the tactics. Any thoughts?
I'll just say that within our group, I think just the brainstorming exercise is great because you get different people with different perspectives, and they all are good ideas.
Yeah. So Harold and I were just discussing while you guys were working that the point of the tactics, of course, is that these are far away from implementation, but that actually is a good thing because we don't, or we should not prematurely commit to an implementation. So this just lets us think about what's the problem that we're trying to face and what's the space of possibilities for achieving that. So Harold was talking about how they actually need to think using these kinds of questions about moving a legacy application to a cloud, and how do you secure that?
We've got, I think, our most interesting things in our third tactic, which was verify message integrity. Because we were looking at different things. I mean, some people said, well, yeah, checksums are like, the most rational thing to do. But if you have a complicated message stream, maybe what you want to do is kind of have like an overlapping parity check for a series of messages that are going across a series of nodes to make sure that you get the whole message through and that somebody hasn't just inadvertently chopped it or maliciously chopped it.
Right.
And then of course if you're going on a different channel, like you're going through email, you say, well, okay, PGP or some other kind of encrypted email is an important thing to have.
Yeah. So that's good. That's a good point. You're going to get different realizations, and depending on the nature of your application, you're going to want to check different things about that message and its integrity.
Exactly.
Yeah, and of course, if you're doing a video stream, well, if a message gets corrupted, no big deal. If you're doing a stock trading, big deal. Okay, so the next part of the exercise is now the mapping exercise. So what we'd like you to do is for teams one, to look at the definitions of two security patterns, security session and single access point, and identify what patterns they're related to. Are these what tactics they're related to. So are these patterns a refinement of a single tactic? Are they a combination of multiple tactics? How do they elaborate a tactic? And document this justification. And JR is handing out the pattern definitions right now. For team 2, your patterns are checkpointed system and audit interceptor.
I'll give you one more.
For team 3, compartmentalization and role-based access control.
Definition.
And team 4, single sign-on and message replay detection. And each of these are drawn from the patterns catalog. So these are well-documented patterns. So again, this is just the summary of who's doing what. So we'll give you about 10 minutes, and then we'll discuss.
So if you'd like to have another copy of the definitions, just let me know. Yeah, okay. Yeah. Anybody else? Okay. Good.
So yeah, okay.
Yeah.
So
So when you're doing this mapping exercise, please these questions, keep these questions in mind. So I just wanted to remind you, that's all, yeah. So just to help your brainstorming, I'm going to hand out actually the answer keys. So let's see.
To help. It was intentional.
So we'll give you a couple minutes just to digest the solution and maybe think of some of those questions we had on the slide. Oh, yeah. So now let's have a discussion, group discussion, based on these questions. So how was your exercise? What were your challenges? And was there any missing tactics? And in addition to this, maybe we can talk about your disagreements. So, so any volunteers?
We'll talk. We'll talk. One of the things is we listed more tactics than you had on your checklist here.
Oh, okay.
And I think part of that was like, well, for single access point, right? The only one you had was the tactic is limit access. But what I think what we were doing was kind of looking inside the box and saying, you know, what does the authentication actually do? And so we had like four more because it's really doing all of these things.
Yeah.
Right.
And in a way, one of them's a good answer, and in a way, the other one's a good answer because it, you know, by broadening the look at it, you know, you're going to be evaluating these things anyway.
Sure.
So I don't think it actually, you know, matters in the analysis when you actually are performing the analysis that, you know, you're looking at a few more tactics. That are somewhat related and connected to the actions.
One of the things you see when you try to implement a pattern out of a pattern catalog is that every pattern is underspecified.
Yeah.
And that when you actually implement it, you probably want to put more stuff in. But the point of the pattern is to capture, or the tactic is to capture the essence and to reason about that essence. And then, of course, you can add on your own decorations to make it fulfill more responsibilities. But yeah, it's a good observation.
Okay. Next thing?
Spokesperson?
Same observation?
Observations that we did find a lot more of these tactics. So.
Oh,
Okay.
Yeah, very good. Okay.
Lindsay, in ours, where we were doing the audit interceptor, there seemed to be a need for some sort of rule-based specification about what events are important
Yes.
to be logged.
Right.
Yes.
And probably another rule-based specification about looking for suspicious
Right.
patterns of usage.
Yeah.
But, you know, I didn't see that as a tactic anywhere.
Right. So in Intercepting Validator, which is a related pattern to Audit Interceptor, If you look at how that is realized, they'll talk about expressing rules. You know, you have some sort of rule specification mechanism, let's say XML, you know, describe them in XML, and then you just keep adding rules to that. So yeah, when you get to the point of implementing that, you're certainly going to have to think about, well, how do I specify these rules? How do I have an open-ended set that I can add to easily, hopefully without having to recompile the system? What was your other point? Look for patterns.
Suspicious patterns of usage.
Right, right. So let's see, would that be a distinct tactic?
Yeah, what I'm thinking is, I mean, some of these more implementation-specific details, those are addressed, I would say, at the pattern level. So tactics are there really for you to think about what needs to be done at the pattern level. And so that was a good, I think, thought exercise, because now you're thinking about what details actually need to be more designed into your implementation eventually, and starting with a pattern. So in that sense, I think it works.
But just on top of what you're saying, I think in our case, for example, the context event processing as one of the mechanisms of using for deciding if we have security problem, is this what we intend to use in our whatever IoT application. So it maybe could be included in the like data analytics, complex event processing can be included as a tactics for the detection part.
Right. So we have detect intrusion, detect service denial, verify message integrity, detect message delay. So there may in fact be more nuances that we would want to capture as an additional tactic. And as we say, we're not claiming that this set is ever done.
Another way,
in fact, that's one of the reasons why we like to do these exercises, is to see what pops up from people's experience.
Another way of thinking about this is also the tactics hierarchy you're looking at. Those are just the types of the potential tactics. So when it comes to the instances of those tactics, there could be many of those instances in different domains. So yeah, that's sort of the starting point.
Right, like your point about verifying message integrity, that it can be realized in many different ways depending on your domain. Is a message, one little atomic bit, or is it a stream of data, for example? That the tactic doesn't really care, or doesn't specify that to that level.
So going back to our point where we over-tactified pattern. So probably the scope of the pattern really matters. So I think that our login stream pattern is much more small scope, where then we put the input validation pattern to help with the chance of SQL injection, for example, in the input box, and other patterns combined to make an overall
Right.
security solution.
Yes.
That's what you did.
So think about using a broker pattern. No one would ever implement a broker pattern the way it's specified in the patterns book. Because if you look at it in the patterns book, there is a broker, and then there's some clients and some servers and some proxies. And well, if I have a broker, then there's a single point of failure. And there is one place that's a bottleneck if we have lots of performance issues. So then I'm going to say, well, maybe what I want is redundant brokers. I want high availability broker. And now I have to add in some availability pattern, like a hot spare or warm spare or something. And then how does one broker know that the other one is still alive? Well, then it needs some ping echo between them, or heartbeat or something like that. So as we start to think about actually instantiating these patterns, we're going to elaborate them with other stuff to address other concerns that we have in our domain. And that doesn't reduce the usefulness of the pattern, because that was our building block, and then we need to elaborate on that.
Yeah, I think the important point to remember is the set of tactics is really a starting point, and you really want it to be refined into patterns so that you get one step closer to the code. Any other comments? Oh, yep.
Oh, we're pretty much out of time.
Yeah,
We're pretty much out.
almost. Okay. So one last question. So go ahead.
One thing that I think we all discussed is a very strong technique for monitoring what's going on in your application is the foundation for all of this. And maybe it's even going further to the infrastructure and the hardware. For many things like denial of service attack, if the monitoring isn't in your hardware, it's too late. Your software is going to reboot because it's completely lost. There has to be some sort of layers in your architecture that refine your security, but at the very bottom, the hardware has to give you half a chance of surviving the denial of service attack.
Sure. Sure. So, and that's part of your job as an architect, then, is to say, well, to do my job properly, the platform has to provide these services or these capabilities. Right? So you're not, I mean, sometimes you don't have that choice. Right? Like Harold was saying, oh, I have to move this legacy system onto the cloud. And it's like, too bad. The system was built in 1994. You know, deal with it.
I just don't see much of discussion about the statistics and the operational measures that you need. That has to be sort of either a set of requirements or a recommendation out of this whole.
So we're not proposing this as a design method. Right? I mean, we have design methods. The idea here was to try and get people to think about what are the building blocks of design, the tactics, and how do those relate to patterns. But you know, your earlier comment about getting the requirements right is obviously an important part of the design process. And your comment here about the constraints from my environment or the degree to which I can specify my environment and manage and control it, you know, that's clearly part of the design process here. So we're just attacking one part of the design, which is how you wrap your head around the space of design possibilities, both from a design perspective and an analysis perspective. And this, our argument is that this gives you a lot of leverage. It's not the end, but if you don't start, our contention is if you don't start with the sort of primitive design concepts, you're often lost in the weeds.
Right.
It's okay to get down to the weeds eventually. In fact, it's very necessary to get down to the weeds, but that's not where you should start. That doesn't give you a design strategy.
Yep.
So, okay, we're out of time. Well, thank you for your participation.